The Big Bang was not the beginning. For nearly a century, we've told ourselves a simple story. 13.8 billion years ago, everything, all of space, time, matter, and energy, erupted from an infinitely hot, infinitely dense point. A cosmic starting gun. But what if that's wrong? What if the Big Bang wasn't page 1? What if we started reading our universe's story somewhere in the middle? The evidence for an ancient, expanding universe is ironclad. But the evidence for a true, absolute beginning is starting to crack. The singularity, that first moment, isn't a physical reality. It's a ghost in our equations, a signpost that reads, "Our physics breaks here." Tonight, we become cosmic auditors. We're opening the books on reality itself to investigate what came before the Big Bang. We'll audit bounces from dead universes, baby universes born from black holes, and cycles that last trillions of years. Our audit follows 3 strict rules. The books must balance on entropy. Why was our universe born so bizarrely orderly? They must balance on causality. Can anything remember a universe before our own? And finally, they must balance on evidence. Can we see the fingerprints of a before time in our sky today? Get ready. We're going to the edge of time, and you might not look at the sky the same way again. Okay, before we explore the fringe, let's audit the mainstream account. The standard model. This is the story you probably know, and it's incredibly successful. It starts with a universe hotter than the core of a star, a seething plasma of fundamental particles. As it expanded, it cooled. Just minutes in, the first atomic nuclei forged themselves in this cosmic furnace, mostly hydrogen and helium. The theory predicts the exact ratios of these elements, and when we point our telescopes at the oldest stars and gas clouds, the numbers match. Audit checkmark number 1. For the next 380,000 years, this universe was an opaque fog. Light was trapped, bouncing endlessly off free-flying electrons. But as it cooled further, electrons and nuclei finally combined to form neutral atoms. For the first time, light could travel freely across the cosmos. That first light is still traveling. Stretched by 13.8 billion years of cosmic expansion, its wavelength has shifted from white-hot visible light down to the microwave spectrum. We see it today, in every direction we look. It's the cosmic microwave background, or CMB. The afterglow of creation. The sky's oldest photograph. And its near-perfect uniformity is audit checkmark number 2. But it's not perfectly uniform. There are tiny, almost imperceptible temperature fluctuations, hot and cold spots that are just 1 part in 100,000 different. These aren't mistakes. They're the most important features in the entire universe. Why? Because gravity is relentless. Give it a slightly denser spot, and it will pull more matter in. Over billions of years, those tiny primordial ripples grew, under gravity's patient hand, into the vast cosmic web of galaxies, stars, and planets we see today. Including us. You are the product of a quantum flicker in the infant universe. Audit checkmark number 3. This brings us to inflation. The standard model has a few puzzles. Why was the early universe so incredibly smooth and flat? Why are regions of the CMB that are too far apart to have ever been in contact with each other the exact same temperature? Inflation is the proposed answer. In the first fraction of a second, a sliver of time so small it makes a nanosecond look like an eternity, the universe underwent a period of hyperacceleration. It swelled exponentially, faster than the speed of light. Imagine a crumpled, lumpy balloon. Now, inflated to the size of the Earth in an instant. The surface would appear incredibly flat and smooth from your perspective. That's what inflation did to spacetime. It ironed out all the wrinkles. But it did something else, something magical. At the quantum level, reality is never still. There's a constant fizz of quantum jitters, particles and energy popping in and out of existence. During inflation, these microscopic jitters were stretched to astronomical scales, becoming those seeds of structure in the CMB. Inflation is the amplifier that took the quantum hiss of empty space and turned it into the symphony of the cosmos. A beautiful theory. And yet, it leads us right back to that ghost. That fracture line in our map of reality. The singularity. So what is a singularity? In our best theory of gravity, Einstein's general relativity, if you run the cosmic clock backward, all the matter and energy in the universe collapses into a point of zero size and infinite density. This isn't a prediction of a real thing. It's the math screaming for help. It's like dividing by zero. It's a sign that the theory itself has been pushed beyond its limits. General relativity is a classical theory. It doesn't include the weird rules of quantum mechanics. To understand the origin point, we need a theory of quantum gravity, a unified theory we do not yet have. That's where the standard story ends. Not with an answer, but with an admission: we don't know. The map is blank. And that is where our audit truly begins. Because there's an even deeper mystery we have to confront first. The mystery of time itself. Why does time only move forward? It sounds like a dumb question, but it's arguably the biggest mystery in physics. Every moment you feel it. Things happen, then they are in the past. But the fundamental laws of physics, they don't care about forward or backward. They're time symmetric. A planet orbiting a star would look perfectly fine if you ran the video in reverse. So where does the arrow of time come from? The answer is entropy. Entropy is often called disorder, but it's more precise to call it the number of ways a system can be arranged. Think of an egg. There is only one way for all of its atoms to be arranged in the perfect, pristine shape of an egg. That's a low entropy state. Now drop it. It splatters on the floor. Think of all the different ways the yolk and shell fragments could be scattered across the tile. Billions upon billions of possible arrangements that all look like a splattered egg. That's a high entropy state. You will always see an egg go from low entropy, whole, to high entropy, splattered, simply because there are vastly more ways to be splattered than there are to be whole. The universe always moves towards the states that are most probable, most numerous. That is the arrow of time. It is the universe simply moving from less probable states to more probable states. From order to disorder. The great puzzle of cosmology isn't why the universe is getting messier today. The puzzle is why it started so tidy in the first place. The early universe had an astonishingly, absurdly low entropy. It was the cosmic equivalent of that perfect, unbroken egg. Any theory that wants to explain what came before the Big Bang must, first and foremost, explain this. It has to explain where the perfect cosmic egg came from. If it can't, the books don't balance. So let's audit our first contender. This idea is called Loop Quantum Cosmology, or LQC. It comes from a candidate for quantum gravity called Loop Quantum Gravity, which imagines spacetime not as a smooth sheet, but as a fabric woven from finite, indivisible loops. Spacetime itself is pixelated. Think of it like a digital photo. If you zoom in far enough, you don't see a continuous image, you see individual pixels. LQC proposes that spacetime is the same. There's a fundamental unit of space, the Planck length, that you simply cannot divide further. This one simple idea changes everything. In general relativity, when you rewind the universe, gravity gets stronger and stronger as everything gets closer, crushing itself to an infinite density. But in LQC, when you get down to the pixelated, quantum level, gravity starts to act differently. At unimaginable densities, these pixels of spacetime create a repulsive force. They push back. Gravity becomes repulsive, not attractive. So instead of crunching down to a singularity, the universe bounces. There is no beginning. Our Big Bang was simply the moment a previous, collapsing universe reached its maximum density and rebounded into a new phase of expansion. The Great Crunch became the Great Bounce. This solves the singularity problem beautifully. It's gone. Replaced by a physically sensible bounce. But what about our second test? Does it explain the low entropy arrow of time? This is where it gets tricky. Some models of LQC suggest that each bounce effectively resets the entropy clock, smoothing things out and creating the clean initial state we need. But others suggest that entropy could build up over cycles. If our universe was just one in a chain of infinite bounces, why is its entropy so low? Shouldn't we live in a much older, messier, higher entropy universe? The books are still being balanced on this one. It's a promising solution to the singularity, but the question of the cosmic egg remains a major point of debate. So, let's move to our next pre-Bang model. A far stranger one. This one comes from the wild world of string theory. It's called the Ekpyrotic model, or brane cosmology. First, you have to imagine that our familiar three-dimensional universe is actually a membrane, or brane, floating in a higher dimensional space, a fourth spatial dimension. Think of our universe as a single sheet of paper in a library filled with infinite other pages. Now, imagine another brane, another parallel universe, also floating in this higher space. The Ekpyrotic model proposes that for trillions of years, these two branes were pulled slowly, almost imperceptibly, towards each other. This long, slow contraction phase is crucial. Unlike a rapid cosmic crunch, a slow contraction has time to iron out any wrinkles or clumps. It naturally smooths and flattens the universe, solving the same problems that inflation theory was invented for. Then they collide. The cataclysmic collision of two entire universes converts their massive kinetic energy into the seething, hot plasma of matter and radiation that we call the Big Bang. Our universe didn't begin from a point. it began from a collision. It's a powerful and poetic idea. A new cosmos born from the meeting of two old ones. And it offers a natural mechanism for creating a smooth, flat universe without needing a separate theory of inflation. But how does it fare with our audit? Entropy is again a challenge. Proponents argue the slow contraction naturally resets the universe to a low entropy state, but this is a contested claim. Did the colliding brains already have to be incredibly smooth? If so, we haven't solved the problem. We've just pushed it one level deeper. And then there's causality. Can information cross the brain collision? Could patterns from the parent universes be imprinted on our own? The math is incredibly complex, but the potential is there for cosmic recall. The receipts, however, the evidence? We haven't found any unambiguous signs of such a cosmic crash in our sky. The Ekpyrotic model is a fascinating alternative, but for now, it's an IOU in our audit. Let's get even bolder. What if the universe is not just bouncing, but endlessly cycling through death and rebirth in a way that's even grander? Let's audit Sir Roger Penrose's conformal cyclic cosmology, or CCC. This idea is mind-bending. It proposes that the very end of our universe becomes the Big Bang of the next. Here's how. Fast forward trillions upon trillions of years into our future. The universe has expanded so much it's become a cold, dark, empty void. All stars have burned out. All black holes have evaporated away through Hawking radiation. All that's left is a thin, featureless soup of photons and other stray particles. In this desolate future, there are no clocks. No rulers. Nothing to measure time or distance with. In such a universe, Penrose argues, the concepts of time and scale lose their meaning. When scale loses its meaning, infinity becomes just like zero. Mathematically, you can perform a conformal transformation. You can squash that infinitely large, cold future down and map it precisely onto the infinitely small, hot point of a Big Bang. The end of one universe becomes the beginning of the next aeon. It's like the final note of a symphony being stretched out for so long that it transforms, without a break, into the first note of the next performance. The cosmos forgets how big it was, and in doing so, is reborn. What an incredible vision! It naturally produces a smooth, low-entropy state, because the conformal mapping mathematically smooths everything out. It passes the entropy audit with flying colors. It's Roger Penrose's specific answer to why the cosmic egg was so perfect. But what about evidence? Can we see ghosts of a previous aeon? Penrose claims we can. He argues that supermassive black hole collisions in the previous aeon would leave faint, concentric circles of uniform temperature in our CMB. These are Hawking points. And his team claims to have found them. However, this is where the cosmic audit gets contentious. Most other cosmologists have analyzed the same data and concluded these patterns are statistically insignificant. They are indistinguishable from random noise in the CMB. For now, the evidence for CCC is highly debated, and not widely accepted. A beautiful theory still waiting for a credible receipt. Alright, let's step back. All of these models, bounces and cycles, propose a serial existence. One universe after another. But our final contender proposes a parallel existence. An infinite number of universes being born, all at once, forever. Welcome to eternal inflation. Remember inflation? That period of super rapid expansion in the first instant of our universe? The core idea of eternal inflation is simple. Maybe it never stopped. Globally, out there in the vastness beyond what we can see, inflation is still happening. Space is still stretching at an exponential rate, an endlessly boiling cosmic ocean. But like boiling water forming bubbles of steam, occasionally a patch of this inflating space will spontaneously stop inflating and decay into a stable, hot state. A Big Bang. A bubble universe. In this scenario, our observable universe is just one bubble in an infinite, ever-expanding froth of other bubble universes. Each one nucleating with potentially different physical constants, different particles, a different destiny. This framework elegantly explains why our universe appears so fine-tuned for life. With infinite universes, it's inevitable that some, purely by chance, would have the right conditions for stars, planets, and chemistry to arise. We simply find ourselves in one of the bubbles that could support us. This brings up an even more speculative idea, black hole cosmogenesis. Some physicists wonder what really happens at the singularity inside a black hole. Perhaps, just like the Big Bang's singularity, it's a place where our physics breaks down, and quantum gravity takes over. Perhaps spacetime pinches off and re-expands into a new region of spacetime, beyond the event horizon. A baby universe. In this view, every black hole is a potential womb for a new cosmos. Universes that create lots of black holes, like ours, are the most fertile, leading to a kind of cosmic natural selection. These multiverse ideas are intoxicating. They solve the beginning problem by making it irrelevant. The multiverse itself might be eternal, with our Big Bang just a local event. But when we bring in the auditors, we run into a colossal problem. It's called the measure problem. If there are infinite bubble universes, how do you make any predictions? How do you calculate probabilities? It's like asking what is the average temperature of all cities on an infinite Earth. The answer is undefined. Without a way to measure, to calculate, to predict, is this even science? Furthermore, there's a powerful theorem by Borg-Goose and Vilenkin that proves that any universe which has, on average, been expanding throughout its history, cannot be infinite into the past. It must have a boundary. This doesn't prove there was a first moment, but it does draw a line. It suggests that even eternal inflation requires some kind of beginning. The audit shows a framework that explains everything and predicts nothing, a ledger with infinite entries but no bottom line. The books just don't close. So where does this leave us? We've audited the contenders. Loop Quantum Cosmology offers a bounce but struggles with the entropy books. Brain collisions offer a natural smoothing mechanism but the causal receipts are missing. Conformal cycles solve entropy beautifully but the evidence is contested. And eternal inflation gives us a multiverse but fails the basic audit of being a predictive theory. No single model is a clear winner. But the investigation itself reveals something profound. The question what came before the Big Bang might be the wrong way to think. Time is not an absolute clock ticking in the background. It is a property that emerges from the universe. The arrow of time is a consequence of entropy. So, asking what came before is like asking what's north of the North Pole. The question itself assumes a framework that breaks down at the boundary. Our human experience is built on beginnings. Birthdays, New Year's Day, the first chapter of a book. They give our lives meaning and structure. But maybe the universe doesn't have one. Maybe meaning isn't found in an ultimate origin, but in the unfolding of the story itself. The symphony is still deeply moving even if you don't know what the first note was. In the end, this cosmic audit brings us back to ourselves. We are temporary arrows, drawn by the universe's great entropic bookkeeping. You are a fleeting, complex, low-entropy structure in a cosmos destined for thermal equilibrium. Physics can describe the arrow, but it is silent on one thing, what it means. In the one domain that truly matters, you hold the pen. Our audit has shown that the Big Bang isn't the concrete wall we once thought. It's a horizon. And while we can't see beyond it yet, we can see the deep puzzles that any future theory must solve. The perfect cosmic egg of low entropy, the receipts of causality, and the hard data written in the light of our own sky. The beginning may be an illusion, but the quest for it is as real as it gets. We've audited what came before, but the laws of physics are just as strange when we audit what comes after. The ultimate fate of our universe, the story of its death trillions of years from now, points to an end so bizarre it makes a cosmic bounce look tame. That story, and that audit, is waiting for you right on the end screen. Now, I need to know what you think. After this deep dive, what's your gut telling you? Was there a true, absolute starting point, or are we just one chapter in an endless cosmic book? Let me know in the comments with one word, beginning or bounce. And if you believe that the biggest questions demand the most rigorous audits, then join our team. Hit subscribe and turn on notifications. We question everything, every single day.